In this video, we're going to discuss Chapter 5, which is an intro to probability. As I said before in class, these next few chapters are going to have a really different feel than the first four, because we're going to get into more of a mathematical feel that I think some of you will be more comfortable in. The first four chapters may be a little awkward or a little different from what you're used to in a course that's offered in the math department. It's still going to be weird, but it will be a little more at home for you, hopefully. So, what we're going to discuss in this chapter are one about how probability quantifies randomness. Now, that's an interesting phrase that I'm going to use a lot because it really describes what statistics does as a field or one of the central ideas of statistics. Next, we're going to talk about how can you find probabilities in different situations. Third, we'll talk about conditional probability and how that relates to the situations that we will encounter in this chapter. Okay, and lastly, we'll talk about applying those rules to sort of objects, statistical objects that we'll talk about in subsequent chapters. So that last point is really a looking forward moment. So first we need to talk about how probability helps us understand how things behave. And another way to say that, probably more sophisticatedly, if that's a word, in a more sophisticated manner, is that probability quantifies randomness. Okay, so we use probability to understand statistics and specifically how to quantify randomness. When observing a small number of observations of random phenomena, the behavior that we see may look different than what we expect. Now, there's a few things that we need to unpack here before moving forward. I talk about random phenomena here, or I use the phrase random phenomena, and I will use it repeatedly because it's sort of a basis of what we do. When I say random phenomena, I mean any event that cannot be predicted before it happens. Okay? So it doesn't need to be completely random, like the flip of a coin or the roll of a dice. Okay? Those are two common things that we'll use in here that are sort of completely random. It can be something that very likely happens, but a random phenomena is any event that we don't know what's going to happen until after it happens. So it could be flipping a coin or rolling a dice, which are sort of completely random, but it also could be shooting a free throw or really any event that we don't know what happens beforehand. Okay, so back to the point that we're getting at here. When you observe a small number of random events, the behavior that you expect may be different from what you actually see. So for instance, if I flipped a fair coin 4 times, what would you expect the number of heads and the number of tails to be? If it was a fair coin and you flipped it 4 times. So think about that for a second. Okay, I hope that most people would say, well, if you flip a fair coin 4 times, you would get 2 heads and 2 tails. Okay, there's some theoretical underpinning behind that idea, but I think that's what most people are going to think. What if I see all 4 heads in the 4 flips of the coin that I did? That's weird, okay, but how weird is it? Or how likely is that to occur if the coin is fair? Okay? That's the important question there that we'll use a lot in this course, is given that the coin is fair, how likely is it that I see 4 heads and 4 flips? And it turns out that it's kind of unlikely, but in fact it's not so unlikely. Okay? And so I ask the question here, does that make the coin unfair? Or does that make you start to doubt if the coin is fair or not? And the answer probably is no, it shouldn't yet. Okay? But as we take more and more observations of these random phenomena, the behavior will tend to somewhere, and hopefully that'll be what you expect. So back to this coin flipping example, if I flip it 4 times and I get 4 heads, that's kind of weird, okay? But it shouldn't necessarily make your mind up that the coin is unfair, okay? However, if I take 1 million flips, okay, so if I flip the coin 1 million times, and only 1,000 of them were tails, then that piece of information should make you worry or wonder about if the coin is fair or not. Okay? Because as you take more and more observations, the behavior of the coin is going to show you how it sort of really behaves theoretically. And if it is true, for instance, in this case, the coin is fair, the behavior should tend to what you expect. And so if I flip the coin 1 million times, I should expect around 500,000 heads and 500,000 tails. Okay? It's not going to be that exactly, but it's probably going to be a lot closer than 0 and 4 after 4 flips. Okay? Then you could extend that to saying if I take an infinite number of flips, then half of that infinite number should be heads and the other half should be tails. Okay? And so this kind of information, or this kind of scenario and setup, leads to a sort of a basis of a definition of probability and what it is. So we're going to first define probability as the long-run proportion of a random phenomena. Okay? And when I mean long-run proportion, I mean I do it a bunch of times, and then I take the proportion of successes divided by all of the trials. Okay? So the long-run proportion of a random phenomena is the probability. So for instance, I've been talking about a lot, tossing a coin is a random phenomena, and then I can get some sort of theoretical probability that that coin is tossed and lands as a head or not. Okay? So I have a few more formal terms that I want to go through kind of quickly here. The first is called the law of large numbers, and it's basically a result that backs up what I was saying in the previous slide. So formally, it says that the observed average that I see of that random phenomena will approach the theoretical average of what is going on sort of behind the scenes. Okay? And so I flip a coin 1 million times and then I look at the proportion of heads. That's my observed average. Okay? Hopefully, as I do that more and more and more, it's going to get close to the theoretical average, which is what governs the process of flipping the coin. Okay? And how does the coin act in a theoretical way? Meaning, theoretically, how often will it flip heads and tails in this case? The law of large numbers says that those two numbers will approach each other as you get more and more observations. And so, along the same lines as my basis definition before, with adding some more formal terms here, the proportion of times that an outcome would occur in a long run of observations is equal to the probability of an event. Okay, so with that law of large numbers, that gets us something and changes our definition of probability ever so slightly. The last thing that we need to think about or understand is the idea of independent trials. Okay? The idea of independent trials is when the outcome of one trial does not affect the outcome of another. As an example, if you flip a coin once and it lands heads, does that affect the next flip. Okay, so hopefully not. There's nothing that says the last flip being heads will change the behavior of the coin in the next trial. That's the idea of independent trials. Okay, and that's sort of central to what we are doing. So we need independent trials to form probabilities. So now I have some more terms. I know this is term heavy at the beginning. Okay, but these are formal terms of probability theory that help us actually find probabilities. And so the first term is a sample space. Okay, and a sample space is important, is very important to these types of problems. So the sample space is the set of all possible outcomes of a random phenomena. And I think it's best described using an example. So if I wanted to flip a coin twice, okay, that was my random phenomena. The sample space is the set of all possible outcomes in that random phenomena. So when I flip a coin twice, what are all the outcomes that could happen? Well, there's heads, 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 tails, tails, heads, and tails, tails. Okay, so there were 4 elements of this sample space. So that's the sample space. It's much like a sampling frame that we learned about in chapter 4, but for like a theoretical version, not for subjects, but for events of these random phenomena. And then it leads us to an event, okay, which is a subset of the sample space. It usually corresponds to a particular outcome or a group of outcomes. So that should say corresponds, not responds. Okay, so for example, event A could be that at least you see at least one head when you flip 2 coins. Okay, and the event, just like the sample space, is listing out the possible outcomes that could happen and describe now this event in sort of words. So at least one head is heads, heads, tails, heads, and heads, tails. So it's 3 out of the 4 events in the sample space. And so event B, another type, could be both tails, and that corresponds to only one element of the sample space. So that's an event, okay? And so the probability of an event is defined in this way only in a special case. And the special case is when all the outcomes are equally likely. Okay? So for instance, a fair coin. Both outcomes are equally likely. If I roll a fair dice, okay, 6-sided die, those events are equally likely. So when that is true, I can define the probability of an event A as this. Okay, and so I've got some mathematical notation going on here. C of A over C of S. This C function is called the cardinality function. Okay, it counts the number of elements in a set. Okay, so this is like a mathematical object. So that C function counts the number of elements in the set. So the probability of an event A is equal to the cardinality of A over the cardinality of the sample space. Okay, so if I were looking for the probability of event A happening in my example above, at least one head, okay, I would start to think about, are all the outcomes equally likely? And they are, yes. Okay, so the probability that I get at least one heads is counting the number of outcomes in the event, which is 3, so that's cardinality of A, divided by the cardinality of the sample space, which is 4. There are 4 possible outcomes in the sample space, so the probability of at least one head is 3 out of 4. Okay, 3 out of 4. So here's a your turn, our first your turn. Suppose that the random phenomena that I want you to consider is rolling 2 fair 6-sided die. Okay, so what I want you to do, I want you to write out the sample space. Okay, it shouldn't be sampling space, sample space. Write out the event that the sum of the dice is at least 7. It should be die, not dice, I'm sorry. Put all the typos. At least 7. And I want you to find then the probability of a sum of at least 7 when rolling the 2 dice. Okay, so that's taking the stuff that we learned in the last slide and applying it here to a different situation.